Balancing Agility and Discipline in Systems Engineering. There is currently much discussion about agility, flexibility, adaptability to change, and similar ideas in the systems world. The term agility is being applied to processes, designs, architectures, and even the systems themselves. Promises of faster deployment, evolutionary capability, delighted customers and users, and fewer late-occurring acquisition problems are irresistible to the resource-strapped, schedule-limited, and continuously harried program managers, product developers, and acquisition executives. However, over the years, we have learned the hard way that discipline is crucial in any complex endeavor. How then do we balance out these needs? Before we talk about balance, we should define discipline and agility. What characterizes each? Why do we need either or both? Discipline is the foundation for any continuously successful endeavor. Discipline can be thought of as following a specific set of rules, looking at the details and making sure that there is alignment between the pieces and the parts. It is learning the basics and practicing them so they are naturally part of your thoughts and actions. It is understanding cause and effect in a task and the underlying principles. Discipline ingrains and strengthens. It involves training, practice, honing skills. It extends and supports natural talent. It allows you to perform even when dealing with adverse environments. Discipline also creates history and experience through repetition. Agility is discipline's counterpart, the yang to its yin, the icing to its cake. Agility is about reacting in the moment, feeling the flow, recognizing and embracing the changes that happen in the environment. Agility releases from habit and invents new things on the fly. It allows improvisation, rapid evolution, taking advantage of variation rather than stifling it. It springs from insight, natural talent, déjà vu. It applies history and experience in new ways. Okay, all analogy and poetry aside, what has any of this got to do with systems? It is abundantly clear that discipline is woven throughout the traditional definition of systems engineering. We like to believe that we can start with a need and a concept, and step by step, box by box, task by task, move in a predictable and traceable way to a successful implementation and fielding. There are rules to follow. The congruency between concept of operations, enterprise architecture, and governance models are a good example. The mapping of requirements throughout the system and the necessity of verification is another. We have tools that lead to rational, defendable decisions. And for many of our systems, this discipline is just what the doctor ordered. So why all this fascination, even adulation, of agility and systems engineering? Well, there are a lot of reasons. First and foremost is failure, or should I say challenge. A decade into the 21st century, and we continue our struggle to successfully build the complex systems we depend on. Systems for defense force multiplication, C4ISR, intelligence gathering and analysis, infrastructure for the economic engines of industry, banking, transportation, commerce, systems that are safe, private, and secure. There are a number of trends that collectively accelerate this challenge. Growing system complexity and criticality raise vulnerability. The ascendancy of software as the preferred solution continues in the face of significant gaps in our ability to understand, validate, and manage large evolving software ecosystems. The increasing speed of technology change, the rapid evolution of threats, and the decreasing schedules for development all lead to the sense that time itself is compressing. Envisioned future systems reflect, embrace, and reinforce these trends. We find that the discipline we have followed is not leading to success. Either we aren't doing it right, or it is no longer the right thing to do. We have to change something. Otherwise, we will simply prove our insanity by continuing to repeat the same process while expecting a different outcome. Enter agility, or maybe just the Agilists, and the Agile Manifesto. I'm sure most of you have seen this, but let's look at it again, this time thinking in terms of systems engineering and the challenges of this century. Note that these are statements that do not say one thing is wrong and another right, just that one side is more highly valued by the Agile community. If you can remain unprejudiced in reading them, these look like common sense. Mostly. There are nearly as many definitions of agility as there are Agile practitioners. I believe, however, that there are some common, key aspects that must be present to capture the essence of agility. As illustrated, these are a learning attitude, focus on value to the customer, short iterations delivering value, neutrality to change, continuous integration, a test-driven approach, a lean attitude, and finally, team ownership of the process. The buzz factor of Agile has created a growing zeitgeist that somewhat unfairly casts traditional systems engineering as a holdover from the 50s and 60s and as a part of the systems acquisition and development problem. Agilists generally view systems engineering as rigid and waterfall-based, overly process-bound, myopically focused on early correctness, and often valuing precision over accuracy and completeness over rapid user satisfaction. They point to the traditional systems engineering V model as it was developed for large systems. The model has evolved over time, but the fundamentals still provide a basis for the life cycle used by defense and other large system developers and acquirers. At the same time, Agile approaches are portrayed as the promised land, praised as a panacea for all the environmental ills. Agility purports to easily deal with rapid change, increased complexity, emergent, vague, volatile requirements, and the seemingly ubiquitous integration and validation problems late in projects. This typical Agile process shows its iterative rather than sequential nature. Now, while an iteration could represent a mini waterfall, that's not always the case, and this is particularly true in risk reduction activities. Of course, neither of the broad characterizations of the approaches is particularly accurate as stated. But they do provide us some insight into the turmoil that has continued to bubble between these two approaches. Regardless of the hype, there is no denying the need for leaner, more responsive development processes and systems. If Agile approaches can be harnessed in systems engineering, it is certainly worth the effort. So how do Agile attributes apply to systems engineering? How can we mature systems engineering to encompass these attributes? Let's look more closely at these attributes and systems engineering and how they might work together. Systems engineering as a learning-based process. One of the characteristics of traditional project management, and by implication much of traditional systems engineering, is the assumption by all stakeholders that foreknowledge is just about perfect. We can define complete, consistent, testable, buildable requirements. Perfect requirements can be decomposed to perfect specifications. Effort, cost, and schedule for the specifications may be accurately estimated. The work can be scheduled according to this information early in the program, and progress can be measured using earned value management or similar techniques. Now, while program managers, executives, sponsors, and funding providers may actually believe this, engineers know that with any sufficiently complex system, particularly unprecedented systems, it is unrealistic to assume this kind of knowledge. As Philip Armour has said, for the most part, engineers do not know how to build the systems they are trying to build. It is their job to find out how to build the systems. That's why systems engineering can be visualized as a set of tools and approaches that allow us to seek information that fills the gaps in the initial descriptions, and in so doing adjust the development to fit the reality of what we have learned. Trade studies, requirements analysis, demonstrations, prototypes, models, design evaluation, allocation analysis, verification and validation. These are all ways to learn about the system that we're trying to build. So, there is no fundamental reason systems engineering cannot be considered a learning process. Unfortunately, the traditional view of the systems engineering V model is often interpreted so that it provides only a limited, one-time-through chance to learn. By reinterpreting the V model from an agile perspective, as we propose a little later, the learning process can be much richer. Focusing on customer value. Systems engineers are often isolated from the customers because their customers are considered fully represented by the predefined requirements and operational concepts. These ostensibly perfect requirements are generally value neutral, with no sense given of their importance in relationship to each other, save some very high-level key performance parameters or possibly some value thresholds within a particular requirement. This puts the learning systems engineer at a huge disadvantage by debilitating an entire dimension of the trade space, the ability to consider the relative value to the customer of a requirement in deciding to defer or relax it in order to meet some other requirement or for some other engineering reason. The trade-off between cross-cutting aspects like safety, security, maintainability, and performance has been identified as the number one risk by a University of Southern California survey of systems and software engineers. The relative importance of the requirements must be interpolated using the engineer's experience, physical constraints, and domain knowledge so that fundamental engineering decisions can be made. How much easier it would be if the requirements were not only clear and concise, but also ranked in terms of importance. There is nothing to prevent including this dimension by having more complete and multifaceted interfaces with the customer. Short iterations. Because systems engineering has been often viewed as a one-pass process, the strict V model, iterations may sound foreign. However, there are ways to do iterative systems engineering. Prototyping, modeling, demonstrations, and testing can all be iterative within an integrated systems engineering and development cycle. Usually, agile iterations should describe a complete operable system with functionality that is valuable to the customer. However, in the early systems engineering phases, deployable operational aspects may not be as valuable to the customer as reduced risk, requirements validation, operations concept validation, interface and interoperability verification, or even technical feasibility. Later, iterations that expand operational capability make sense, but only if the systems engineering activities are aimed at accomplishing them. Development processes, where systems engineering is seen as an upfront process, and the systems engineers complete their trades and decomposition tasks and then move on to another program until needed for validation. This is sometimes referred to as the do it once and the systems engineers do lunch approach. These are not conducive to iterative work. One of the most creative ways of envisioning systems engineering iterations is Barry Bain's characterization of systems engineering as a command control, intelligence, surveillance, and reconnaissance activity, consisting of numerous observe, orient, decide, act, or OODA loops, and ongoing intelligence, surveillance, and reconnaissance tasks. This counters the traditional cycle of requirements, delay, and surprise. Neutrality to change involves the architectural and design approach more than pure systems engineering, but unless systems engineering performs its activities and processes with an eye toward supporting change rather than avoiding or denying it, change will become an enemy rather than an annoying but faithful family member. Already, systems operational concepts and enterprise architectures are being defined as evolving and are required to represent multiple stages in system developments. This recognition of temporality inserts change as a dimension in trade studies, leads architectural review evaluation criteria to include ease of modification or extension, and even adds requirements and design constraints that support change neutrality. Continuous integration and test-driven development. Once the idea that systems engineering iterations are feasible, then continuous integration and test-driven development are not as problematic. In order to provide an operable system that demonstrates value, there must be ways to maintain the configuration over time and use it as initial validation of operational capability, interoperability, and interface quality. Most likely done in a simulated or hardware-in-the-loop environment, frequent integration and requirements-based testing, especially where there are external components that you may or may not control, can identify anomalies, misinterpretations, and downright errors in the interface specifications or the implementations much earlier than traditional late-in-the-process integration. This does require a change in the once-through V model, as we discussed earlier, but it can be thought of as a concurrent execution of processes within the V model framework. One way to think of this is to agree that the processes that define the V model are only required to complete in the order they appear, rather than to always proceed sequentially. Lean. Lean, as I interpret it here, is removal of low-value or unneeded activities, delay of significant end-user decisions until the latest possible moment, and recognition of the value of flow. We've talked about rethinking some activities to make them more useful, and certainly most tasks have some fat in them somewhere. However, delaying decision-making in systems engineering doesn't seem quite as easy. There is a drive, often due to contract language concerning progress payments, to complete specifications, finalize allocations, set architectural structures as early as possible. This is also critical when there are long lead manufacturing items in the mix. Remember, though, Lean doesn't delay all decisions, just those with significant impact that can be feasibly delayed. Once you lose the early omnipotence syndrome, delayed decisions can retain development flexibility longer, enabling more rapid reaction to internal or external changes. A focus on flow asks the engineers to perform their activities in small work packages that can be aggregated in different ways so that the delays associated with critical path are minimized and resource utilization maximized. Team ownership of processes. This may be the most controversial Agile attribute in a process-focused organization. If the systems engineering team owns its own process and can manipulate it to meet the project needs, how then can the quality assurance folks ensure that the correct process is being followed? This depends on a decision by management to support empowered teams in more than name only. While it may disappoint some of the stakeholders, providing the systems engineering team with the necessary authority and flexibility can radically change their effectiveness. A relatively straightforward way of balancing agility and discipline is summed up in the following question: is it riskier to do this more traditionally or with agility? Each approach has risks and benefits. In their book, Balancing Agility and Discipline, Boehm and Turner identified some of the key risks to consider in engineering a balanced development strategy. As shown, these risks include environmental, agility, and plan-driven risks. By comparing the risks and benefits, it is usually possible to make a call. If it isn't, you might need to buy a bit more information about the activity in question. Once all risks are evaluated, it is possible to develop an appropriate life cycle and organizational structure, identify useful early architectural patterns, and monitor the systems engineering process and activities to watch for any of these risks arising. The role of software is a good example of a significant systems engineering issue that requires adjustments, if not agility, from systems engineering processes. As systems become interdependent, that is, where software provides most of the functionality and is critical to most of the non-functional requirements, the need for software as a full participant in systems engineering becomes critical. The days of software coders carrying out specific instructions from engineers are over. Software is what enables flexibility, undergirds net-centric operations, and allows quick response to new threats and environmental factors, much of the agility we are striving for. Initial decisions must consider software architecture, or they can impact the feasibility of software solutions and result in disjoint, untestable, and unmaintainable software components. If software is considered a primary player, the systems engineers can take advantage of the flexibility and adaptability of software, define the system and its components in such a way that software development is less complex, the system's architecture and design support the critical ilities, and operational and technical flexibility are enhanced. It is more and more evident that traditional systems engineering may not fit today's and tomorrow's systems because of its inherent rigidity and its usual interpretation as a waterfall. On the other hand, agility is much more a state of mind or philosophical approach than a set of rules that have to be followed regardless of appropriateness. Despite the disagreement from true believers, process is not the enemy. Bad process is. To encourage agility, processes should not be dictated by the process police, but be under the control of the actors. Process experts can provide constructive support and guidance when needed, and process asset libraries should include agile or agile-friendly processes that can be used where the development environment or the risk profile indicates a need for agility. The fundamental goals of systems engineering have not changed. However, as systems grow larger and more complex, new ways of dealing with abstraction, concurrency, and uncertainty need to be developed. Agile approaches do offer reasonable and elegant ways of evolving systems and software engineering towards handling these issues. Finally, as Fred Brooks has said time and time again, there are still no silver bullets. But we can accept that agile concepts may provide us with new kinds of regular bullets and new tactics by which they can be fired. There is a good possibility that integrating these into current operations can significantly improve the capability of existing systems engineering arsenals.